this lesson, we learn how to use the stoichiometry flowchart, how we can get one unit to another unit using the concept of conversion factors. In this lesson, we are going to look at molarity, and how molarity is not just an equation equal to the number of moles of chemicals over the liters of the solution, but we look at it in terms of conversion factor. First of all, molarity is a unit of concentration of a substance in a solution. That is, if you have a solid substance and you put that substance in a solution, or specifically distilled water, now that solid will dissolve and make a solution. And of course, the more of the solid substance you add into a fixed amount of water, it will become more concentrated. And that is, when the molarity is high, you have concentrated solution. When the molarity is low, you will have less concentrated solution. So, smaller number of molarity is less concentrated. That means you have less number of moles of that substance or less mass of that substance. Where when you have a very large number of molarity, it is more concentrated. That means you have more number of moles of that substance, or another word, in terms of mass, you have more of that substance, but a very small amount of volumes. In this lesson, we are going to look at molarity not just as M, but more specifically is the number of mole A over 1 liter of solution. And sometimes we abbreviate solution as SOLN. Okay? So let's look at this in terms of how can we solve this. And also we need to define solution. What is solution? Solution, of course, is going to be the solid substance or whatever substance that we dissolve in the solvent. So solute is basically the substance that's being dissolved, and solvent is doing the dissolving part. Like, for example, water. If we put table salt in water, the salt itself is the solute, and the water is doing the dissolving. So therefore, what we have here is water is our solvent. Let's take this up to the next level, where we have to use this basic concept and the stoichiometry flowchart to determine the product that will form in a solution. So first of all, what we have here is a solution of 0.06 liter of 0.322 molarity potassium iodide is mixed with 0.02 liter solution of 0.530 molarity of lead nitrate. And the question asks you for how much of the precipitate will form from this reaction. Before, when we do stoichiometry, we are given the chemical reaction. And in this case, we are looking at specifically precipitate. So we have to apply a solubility rule. So this is the next level. In this case, we have this right here, potassium iodide. So potassium iodide, right there. And this is going to react with lead nitrate. So we have PbNO3, 2. So the way it works is that we have to apply the solubility rules to determine what precipitate are we going to make. So we have to determine the ions first, and then the same thing for this one right here, Pp2 plus, NO3 minus, and of course we exchange ions, there you go. This one is lead nitrate, and we look at the solubility rules, lead iodide is insoluble. So we have our precipitate there, where potassium nitrate, it is in group 1A right there, so it's soluble. So this will become spectator ions. The potassium and the nitrate, they are spectator ions. They don't involve in the chemical process of making the precipitate. So our precipitate in this case is Pb, which is 2 plus. Okay, keep that in mind. Pb2 plus, and we have iodine minus. So we have to crisscross to determine the compound. In this case, it's going to be PbI2. Of course, we have to think backward to determine what are the reactants going to be. Of course, it's going to be Pb2 plus in aqueous state. And we have iodine also in aqueous state as well. Because we have 2 iodine here, we need to put a coefficient of 2 to balance out the chemical equation. So let's make this even nicer. We rewrite this Pb2 plus aqueous plus 2 iodine aqueous. And that produces the precipitate that we are going to measure. So we have a chemical equation that we can use the mole ratio to apply to our stoichiometry. Now, the first part we have to realize that we have 2 sets of reactant, this one and also that one. So we have to apply our limiting reagent. So we have to take our reactant in form of solution, convert it to the product right there. Now let's go back to the concepts of molarity. So molarity is a conversion factor. Basically how it works is that if we have a solution with a specific molarity, we can use this conversion factor to solve for mole. And once we have mole, we can do anything with the stoichiometry flowchart. In this case, we are looking at the number of grams of B, which is our product or the precipitate. So the way it works is, let's solve this problem together. Let's look at the first one together, okay? And the first thing we have to do when solving this complicated problem is doing one reactant at a time. We know that we have 0.06 liter, which is our volume, and the molarity is 0.322. But don't think of molarity just M, but think it in terms of number of mole. A, in this case, what is A? A is Ki2. And over how many liters? Of course, it's going to be 1 liter of solution. And the number of mole, we know exactly how many mole it's going to be. In this case is 0.322. Now, using this together, we can actually look at our stoichiometry flowchart. Notice how we have solution volume, right? That is that one right there. So we're going to multiply that conversion factor to get a mole. So what we have here is 0.06 liter of solution times the molarity conversion factor. In this case, if this is liter of solution, the liter of solution will be on the bottom, specifically 1 liter of solution. Because anything over 1 is equal to self, and the top part would be 0.322 moles of Ki2 right there, potassium iodide. And that would give us a mole. And once we get a mole, we can now convert to moles B using the chemical equation right there, and convert to mass using the basic molar mass. So let's finish the problem. And if we look at the net ionic equation, notice how the reactant lead and iodine, they are both ions. But our given reactant, they are in compounds form. So the way it works is this. We need to realize that lead iodide is coming from lead nitrate. So that tells you we can use lead nitrate to represent lead ions. The same thing with iodine. Notice how iodine ions is coming from potassium iodide. So instead of using iodine, we can just use potassium iodide to represent the ions of iodine. So that's a lot of things we have to look at. So what we have here is the solution cancel out. In this case, solution of iodine cancel out. So what we have here is moles of iodine. But the chemical reaction does not have moles of iodine, but we have that right there. And it has a coefficient of 2. So again, we can use this to represent that. In this case, we have 2 moles of potassium iodide. And this is relative to moles of B. What is B in this case? B is going to be the product that we look at right here, which is your precipitate. In this case, the coefficient of the precipitate is 1 mole. There you go. And now we have the mole of precipitate. Of course, we can solve for the mass of precipitate using the molar mass. In this case, we have 1 mole of Pb by 2. The molar mass 461.00 gram of Pb by 2. And the moles of Pb cancel out, and the moles of iodine cancel out. Give us our mass of Pb2. And we plug into a calculator, and we have 4.45 grams of lead iodide. So that's for one reaction. Because we have two different reactions, so we have to look at the second reaction to determine how much of precipitate will form from this given amount of reaction. So we have 0.02 liter of solution of 0.530 molarity of lead nitrate. So let's plug into our stoichiometry flowchart. Of course, our solution in liter would be 0.02 liter of solution. And using molarity as a conversion factor, instead of thinking this as just M, but this is actually equal to 0.53 moles of lead nitrate over 1 liter of solution. So what we have here, of course, is going to be the liter of solution on the bottom, which is 1, and the mole will be on top. But if we look back at our net ionic equation, we don't have lead nitrate as our reactant. But we know the lead ion is coming from lead nitrate. And we can use the coefficient of our net ionic equation to apply to there as well. So in this case, it's going to be 1 moles of lead nitrate to 1 moles of lead iodide. And now we have moles of the precipitate. This is cancel out. That's cancel out. Multiplied by the molar mass of potassium iodide. So the last step is to convert our moles of the precipitate to the gram of precipitate. In this case, it's going to be the molar mass. And we saw that molar mass somewhere right here. Oh, it's right there. So 1 mole of lead iodide. And then the molar mass is 461.00 grams of lead iodide. And we plug this into our calculator, and we would get, of course that cancel out, and we would get this number, 4.89 grams of lead iodide. So we have two different reactions that produce different amounts of the product, or the precipitate. But which one will be the accepted values that's going to be produced in the chemical reaction? Of course, it's going to be our limiting reactant. That is, the reactant that produces the least amount of the product, which is this one right here. So this is actually how much of lead iodide precipitate we are going to make if our reaction is 100% efficiency. And that is how we apply molarity, stoichiometry, and limiting reagent into one single problem.